we're back, and we are doing the same thing we did yesterday. We're doing matrix calculus. We had the brilliant click from Vault Chat yesterday in the notes. I started this video cold, so my brain is not primed to be doing calculus yet, but we're going to go straight into it while it's still light outside, while the natural light is still sufficient to actually, you know what I mean? Like I don't need the office lights to for me to be lit. You know what I mean? So awesome, fantastic, and let's get right into it. Let's see. Exit full. So once again, I tried to prepare in advance. Um, Interestingly, or I don't know about how interesting it is, but fun fact, this time I took it a little bit further, or I'm taking it a little bit further. Um, Last time we had an issue where on my screen I have the 16 by 10 aspect ratio. So I had my drawings all the way down. So if I drew something down here, you can't see that I just drew a circle. You know what I mean? Um, to fix that, that's because I have this bottom right panel. Um, I have it expanded all the way down, but technically, I don't have to do that. It looks a little bit weird for me because now there's just this empty space in the bottom right hand side of my screen. And actually, what if I take it further? I'm only realizing this part just now. What if Vault Chat also fit higher up? This may be a little bit harder because it's an actual window. Let's see. Oh, look at that. So now there's nothing that I can see. Now there's just like a black bar at the bottom of my screen. It's just like a dead screen. But now I see exactly what you see, which is fantastic. So when I draw down here, what? How can you not see that? Oh, is it an aspect ratio issue? That's really unfortunate. Let's see. Yeah, so if it gets too narrow, it's just gonna crop. So let's see. If that's the bottom of my screen, I'll make myself smaller. Yeah. Now you can see everything. So that's the actual ratio of my iPad. And then I'll make myself smaller. That's fine. Okay, perfect. So that is, oh boy. Ah, we're not gonna look at that. So this is now you have like every corner of my iPad, I think. Let me do the corners. Perfect. Fantastic. So what's it called? I can draw anything and you guys are gonna see it. Beautiful. Um, so where do we leave off? Let's go into Vault Chat. Um, we have back prop exercises. The big hoorah was this. Um, and we didn't make it to the neural network. Holy moly. Um, we're making it through the neural network today. We have to. Because today's Thursday, and like, yeah, I wanted to code Friday or the weekend. So, best case scenario, we make it through the LLM today, and we start looking at Karpathy's mini GPT or nano GPT. Start reading the code. Um, let's see. I'm not doing the derivative across entropy loss. Maybe I can. I don't know. It is pretty simple with respect to A. Okay, it's y over A plus 1 minus A over Y minus. Yeah, I think that might that might just be it. This is just fully scalar, so it's irrelevant. And then oh, negative. Yeah. Oh boy. Oof. Okay, yeah, calm. So let's see. Where do I fully want to start? The big thing that I want to click is this. So do I read it or do I try to exercise it? It's like this transition towards the end. It's like this is actually exactly the outer product. Yeah, this is the definition of an outer product. I need that to click. I read it and I was like, oh, it's right, but it's not in my head yet. So yeah, maybe I don't know, maybe I just read it again. It's like, okay, your work, self-test 2. Let's write out the scalar chain rule for a single weight. Ah, I'm starting to remember what I did. No, let's draw it out. Let's draw it out again. because I would like to have to recall it. So we are doing the case of mean squared error because its derivative is so nice and easy. Mean squared error loss for logistic regression, and we're going to go from single head logistic regression because softmax to multi-head logistic regression, and we're going to see the relationship from the actual down to the single gradient level and motivate or give context to the use of the outer product and the shape of everything. Very important. So let's see. Very first thing we have is y hat. It's still too big. I don't like that the default is 8. I think I want to make the default. I'm not going to because, how do I say it? I need to stay away from vibe coding for a moment and like actually just like use the things. Let's see. So y hat equals, oh, but that doesn't matter. We only care about loss. We don't even care about y hat. So L equals y equals 1/2 y minus a squared. And then a equals sigmoid of z, and z equals wx plus b. A and z are intermediate variables. So I've sort of been saying that a is like the key intermediate variable, but it's actually, we're going to do L with respect to a with respect to z, z with respect to w, and then we're going to chain that. I'm not going to. It's too much pure math for like just like a single video, but like yeah. Let's see, is partial derivative of L with respect to w equals the partial derivative of L with respect to a times the partial derivative of a with respect to z plus times the partial derivative of z with respect to w. Now, this works completely fine for the scalar case, the pure scalar case, but that is not the case we are in. And that might be why going to this will make sense, will be more correct in a way. What's it called? This is fine for scalars. Okay. Let's see. W is a scalar. Now what happens if W is a vector? Now we have W equals, or no, that means W is a 1 by D vector X is a, nope. How do you draw the fancy X? I'm not there yet. I don't think I'm there yet. No, I'm not locked in enough to be doing that. Okay. Let's see. Is X is D by 1, which makes it a column vector, which is important because we discussed this, which means that B is a scalar. 1. I don't know if that's the right way to represent it, but sure. Sure, we can give everything else parentheses. Okay, so that means L with respect to W must also be 1 by D. It must be, because it's L with respect to all of the contents of W. It's a sort of a matrix. So how do we write this? In the scalar case, what's it called? L is still a scalar. A scalar. Z scalar. But W is not. So a scalar with respect to a vector, we'll end up with the X transpose. That's me cheating, I know the answer. Let's spell it out. Is that ZJ form? Let's do this. This is all the same, but now Z is a scalar. Oh, yeah, it's a dot product. Okay, cool. Z still equals W1 X1 plus W2 X2 dot 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 WD XD plus B. And that's Z. And therefore, the partial derivative of Z with respect to W equals X1 X2 dot 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 XD, which equals X transpose, because X was defined as a column vector. Again, that transition, the fact that we are saying it's a row vector, to each his own. It's a notation, and I don't do linear algebra so much that I assume that it's going to become a row vector. And there's across, like, how do I say, across spaces, like, maybe in stats, I would write vectors as rows, and like in machine learning, oh, you assume vectors are columns. So like I've had professors like mix these things up, and that's the word. There's no discipline that I strictly follow. So yeah, that's fine, and that's good. So now we have, and then it's the same thing, is partial of, how do I say, of A with respect to Z still equals sigmoid of Z 1 minus sigmoid of Z, which equals A of 1 minus A. Did I say that's with respect to Z? Okay. And then once again, L with respect to A equals, what's the word? Y minus A. Beautiful. So, yeah, we're going to multiply. So if it was 0, the gradient, it wouldn't matter. Okay. And it's how much the weights. That's sort of curious. The significance of the weights is, oh, but it's scaled by the activation. What's A? How did we produce A? Sigmoid of Z for the weights that we changed. Yeah, no, it's too complicated now. It's confounding. That's fine. This is a scalar, this is a scalar. We'll multiply it all out. The A is from the instance. So we know A. If we did a forward pass, we would have A. And that's part of doing the autograd graph. So that's W being a vector. Now, this was our key unlock. for W being a vector. Now, what if W is a matrix? Now we have W is M by D, where M is the number of heads. Could do H, whatever. And we still have X is still 1 by D. Or is it D by 1? We said it's a column vector. And that means B is, how do I say, is a column vector. It's 1 by M? Surely not. I mean, it's M by 1? Surely not. But I believe it is. Yeah. An M by D matrix multiplied by D by 1 vector produces an M by 1 vector for which you add B M by 1. Fantastic. Okay. And then what was the next step? So in this case, again, math is weird. And because I'm like sort of self-teaching, I don't strictly know what to do. For example, is like I can do something that may work, but it may not be best. But then also that could be like my edge. So it's a risk, and we're taking it here, obviously. Full display. And let me like, I don't know, spell out the risk is like, it's a very here, connect the dots understanding that I'm using to make this work is like, I'm going to then, I'm going to follow up and say that, oh, well, because of the shape of this and the shape of this and the shape of this, well, this must be, this must be, this must be. But that's not, it's like I'm deducing information instead of producing information in a way. And that deduction is easier than deep comprehension. And that deep comprehension, I am putting off for now because what it requires, I believe, is quite deep. I would like to be wrong, and maybe I should find out, but not right now. Let's stay focused. So L is going to be a vector of shape M by 1. And how do I say? A, the activation, is also going to be a vector of M by 1. And Z is also going to be a vector of M by 1. Scalar, vector, vector. Perfect. That's what we expect. And then we can move it to the side. This case, it's not X transpose. It's, how do I say? For at least the partial of Z with respect to W, it's X1. How far can I do this? Oh yeah, XM X one XM. Wait, how do I denote? Wait. Wait, what? Wait. There's no XM, but there's M of them. Let's see. I'm like extremely bad at drawing the. I don't even know what the shape is. Maybe today's the day I learn it. That shape. I'm very bad at drawing it. Okay. This is M. And this is D. Yeah. and you would get, it's still going to end in D, which is why this is redundant. D. You get a matrix. M X transposes, because for logistic regression, it's indifferent. It's the same thing, especially even more so because sigmoid is performed element-wise. I'm curious when we get to the neural network and the LLM, what happens when it's softmax and it's not performed element-wise. How do we change our operations? So, okay. So, we're choosing to go all the way to the end. Is like, for the pattern that we've been following, is now I can look at this. Is we have J, Z is a vector. There's M of these ZJs. Okay. And that equals WIJ XI plus, I would just do 1. Yeah. See, like, I don't have to follow what VaultChat writes. This might be even easier for me to see it as. If I just do W1 X1, no, W1J. Oops. It's row column. Ooh, does that matter? How would I know? W has M rows. So that means WJ. Oh my goodness. WJI. WJ1. Goodness. X1. Not XI. Plus WJ2 plus. Oh my goodness. Times X2 plus dot 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 plus WJD XD plus BJ. Okay. Yes. And in fact, we have a stack of these, exactly M of them, which means, so now we can write, how do I say? So Z with respect to actual W equals this matrix, for which it is for, oh, interesting, is because we're indexing both J and W. Interesting. Because J is a vector here. So for every row, for every row, and this is a choice on shape, is we want the derivative to be the same shape as W because we're going to do the, how do I say? We're doing the denominator notation so that we can do descent. Backprop, what's the word? A gradient step? I don't know how much I've been glitching. I really hope this hasn't been like a consistent thing. What's it called? We want it to be the same shape as weights because it's a perfect map. Okay. So since we have that, it must be M rows and D columns. And if it's M rows, then it's for every row, it's the vector version of that ZJ, which is actually just X transpose. So we can write, I would do this. I would do it's X transpose, because across them, notice that these X's are invariant to J. So we have a whole bunch of X transposes, which is equal to, let's just go with this. Perfect. But that's interesting because J is a vector and W is a matrix. So like, but in the other case, yeah, but we only care about the shape. We only care about following the shape of W, I guess. Like, could you do a matrix with respect to a vector? Like, I wonder if like could the denominator be smaller than the numerator? I don't know. You know, some questions are like too hard to ask because the tangent would take you too deep in a particular direction. I'm too scared to ask that. Um, okay, so um that gives us the partial z with respect to w. However, very important, and this is where we can finally start leaning on what VaultChat wrote, is yes, is we're going to do this, is oh, L, wait. How dare I? I said L is a vector. Why do I think L is a vector? Why is L a scalar? Are we sure? Are we sure L is a... Are we sure L is a scalar? For mean squared error? That would be element-wise. That would absolutely be element-wise. L would be a vector, not a scalar. But Lj is a scalar. So that's how I would prefer to write it. That makes more sense to me. And like, um, we have from J until M. No, M. I don't even know if that makes sense. But like J is indexing the number of like heads. So with respect to, and I really like this, I really like taking it down to the scalar level, is like the, for head J, weight Wij affects it how much? And I would love if I can recall it without looking, is going to still be Lj over Aj times, and because we're scalar, it must stay the same. Aj over, I think we agreed, is that they're in the same shape. Zj, A with respect to Z, times partial of Zj over Wij. Ooh. But it's technically Ji, given the way we've written things. So Wji, and we could do Wj and call this a vector, and then scalar, scalar, and then concatenate it to be a matrix. Okay. Let's see. Hmm. Hmm. But they're synced. So this is still, no, this is a scalar. Nope. Come on. This is a scalar in a vector addressing what element, what head, what zi, or what zj activation these weights activated. These are a bunch of, how do I say? This is equal to x I. That's what that's going to be equal to. Now, just recalling what VaultChat had said is, interestingly, these two how do I say, are both of the shape, are both purely indexed by j, and have shape m, which means that they are a Hadman product. I don't know. How would I write this? L with respect to a is y minus a. How would I write that? I would have to write it like, yeah. I would have to write it like, wait, no, then I would get rid of the j's. And then I think, yeah, I already peeped, which is the same as writing it as. Okay, but also, something I'm messing up is, what's it called? They've done this, but I've been writing things in terms of j. Oh, epic! Epic! I recalled the xi. I was confused on this. That's good. That's good. Did I erase it? Aw. Yes, I'd said that this equals xi. zj, wij. Perfect. Okay. So, equals, yeah, times xi. Notice how the first two terms depend on the class index j. We can group them together into a single scalar. Okay. The thing that I'm messing up is that I'm not calling L a scalar. Yeah. Because I'm not calling L a scalar. I'm curious if that's doing anything. I guess technically if L isn't a scalar, there's still the same number of things. It's just, instead it would be with respect to the same number instead of each of them having their own slot. It's almost like a pyramid. How do I say it? It's like this instead of this, where we have a, I don't know, AJ, AM, and this is LJ, LM. You know what I mean? I've been drawing it like this, but the VaultChat has drawn it like this. Oh, well. But yeah, in that overlap is the fact that everything is still being indexed from J to M. I don't know how big of a deal that is. So it means you can write it as a scalar, but you can turn it into a vector. Okay. In vector notation, yes, is the element y is Hardeman product of our two upstream vectors. I think it's a vector either way. L with respect to A. I would still capture it as a vector because it's all of the losses of L. Is it the fact that you would sum it afterwards? Is like you have the loss with each element and then you just add? I would do that. I would just add. So loss is always a scalar. I'm cool with that. I can follow along. I'll get behind that. And then yeah, perfect. Vector, vector. And yes, so that means this vector. Yeah. Now our scalar derivative still goes back to this vector. No, this element of this vector times this element of this vector. However, it's by I and j. Once again, making it an outer product. So it's this by X transpose. And then we defined this as L with respect to A by A with respect to Z. And those are element by element, but then this one is an outer product. Why is it an outer product? That's the, how do I say? That's the gap in like the deep understanding for me is like on the scalar level, I can operate. I can operate and understand what's going on a scalar level. But I wouldn't think I'm not so fluent in linear algebra that I would think, oh, take the outer product. You know what I mean? It's like, oh, we have these two, so we should take the outer product in order to make that align. And that grouping is like a, how do I say, to produce this delta is almost like a convenience thing. Because well, what if you didn't want to do it in that order? Because multiplication is cumulative. So what if you wanted to do, you could do the outer product with sigmoid and x, because it's still an outer product, I guess it must be. And then you would multiply this outer product matrix by a vector, but then you would get a vector. So how would you multiply? How would you retain the fact that you need this to be element-wise, you know? So the order of operations, I have yet to become fluent in linear algebra. But yes, I'm okay with that. That's our recap. That was our first 30 minutes, low key. But that was good. That was good repetition practice for me. I'm also noticing that this is like not in sync. Wow. Oh. Yeah, I guess you can just turn off. Okay. Yeah, no. I really hope that that's. I really hope it hasn't been too out of sync for you. Um, okay, on to the neural network. Context. One, feed one linear plus activation layer into another. Every operation here already appeared in rung 2. The only new question is how gradient crosses join from the second layer to the first. Okay, so W1, B1. Yes, layer 1's weights and biases is heads for. Ooh. H doesn't mean heads. Oh, it's the hidden layer dimension. Okay. Hidden layer dimension by X input dimension. Yeah, hidden layer. Interesting. Your bias is in your hidden layer dimension. Makes sense? Layer 1 pre-activation, hidden vector of shape H. Perfect. Yep. Yep. is M, which is your output. So your number of heads. Yep. And then our output. Yep. And activation derivative element wise. Why would we take this out? Are you hiding this from me? Are you telling me that it matches M1? What? That doesn't make any sense. Whatever. Tool introduced here, the upstream gradient. Interesting. Defined delta of L for the layer is equal to the gradient of L with respect to a layer's pre-activation. L with respect to Z for the layer. Upstream gradient. Upstream gradient delta, okay? Backprop then becomes compute delta at the top, then hand it down. Each layer takes the delta arriving from above and converts it to the delta it passes below. The layer 2 step is literally the rung 2 problem again. The layer 1 step is the rung 1 problem a second time, fed from whatever layer 2 handed down. Tool introduced here, the important one. What? When did W become transposed? It wasn't transposed here. We didn't even have W in it. Let's see. Tool introduced here. Why W becomes W transpose going backward forward. Layer 2 sends the hidden vector up. Now stated generally. Descend gradient back down to A1. You gotta slow down. Forward, layer 2 sends the hidden layer up through W2. This isn't true. Where's the bias? And why did my iPad disconnect? Descend gradient back down to A1. What does that mean? You apply the Jacobian of the step, and by denominator layout, that Jacobian is W2 transpose. It's not clicking. English out loud, not too helpful. Maps input to output, sure. Maps output grad to input grad. Sure, maybe. If we're multiplying things, sure. But not if we're stacking gradients. You know what I mean? So the handoff onto the hidden layer reads. This might take the rest of the 30 minutes. You're running the rung 2 steps twice, joined by the delta handoff. Name out loud which part is rung 2 again, and which part is genuinely new. Hmm. Guys, I'm confused. I'm completely spaced out. I was looking at words. I'm not following anything. I don't know what's going on anymore. none of this makes sense. So let's go back to our roots and let's see if we can do it ourselves. So forget, because I know what a neural network looks like, but I don't have the tools. And a neural network should be a very similar shape to logistic regression, very similar shape. So I'm instead going to go with, let's take what we learned and internalized here and simply extend it into a neural network. So what does a neural network look like? We have L. What type of neural network do we want to build? Let's do a single layer. I mean, a single hidden layer. Let's not overcomplicate it. And sure. Okay. So, but we don't want to give it numbers. We're using this to, how do I say it? For mental imagery. Yeah, guys, we're working with neural networks today. Oops. What am I missing? Sure. That's our neural network. This is X. Oh, I've forgotten to draw. Let's see. Is that how we would do it? I think that's how we did it in my elementary applied linear algebra class. Oh, where'd the line go? Sure. So this is X, this is H, this is B1, B2, and then this is A? Yeah, just following VolChat. So we're still gonna do mean squared error just because it's so much easier. Is L equals Y minus A squared. Nope. Oh, however, because we have moved to vectors, we're going to say is it's the sum okay, from j equals 1 to m of yj minus aj, which is simply the element by element sum of loss if it was a vector. That's technically what loss is. So that's what loss is, and then A equals sigmoid of Z. I don't think that's changed. I think we can call it Z2 is that's the pre-activation. Do we want to say this is A2 then? Then we can't do it like that. Yeah. So A2 equals the element by element sigmoid activation of Z2. Nothing's going to be squared. We're not going to mix up our superscript. We're not. So that's A2. This could be miserable. Notation hell, bro. So that's our second activation. Equals sigmoid of Z2, and then Z2 equals W2 H plus B2. H equals, well then no, it's Z1. So nobody's naming H. Is Z1, nope, of A1. That's why. Perfect. And then, do we want to go purely horizontal? Or are we going to keep going? Let's see. A1 equals sigmoid of Z1. Z1 equals W1 X1 plus B1. It's not X1, just X. Okay. Which is why this is like so familiar. This is like so similar to what we've already been. Oh, you can't see it. This is so close to what we've already been working with. Oops. You blipped. How did that happen? Okay. So this is most everything. And then how would this flow through? We want to get, what's it called? I want L with respect to W1, L to W2, L with respect to B1, and L with respect to B2. Cool. These are the parameters that we are going to control in our neural network. Oh boy. So like, oh, come on. You know what I mean? Like math. This is why this is like applied math, you know? Because like there's so many things that you can write as like true, that are true in math, you know? You know, like math permits it, but applied math is pure math with motivation. Maybe a pure math person would probably hate that I said that, but yeah, it's like, you know, the application, especially in this context, you know what I mean, is the application is motivated by us wanting to train a large language model. So let's just like off the top of my head do like the first one. Is L with respect to W1 is going to be equal. Let's not even do it in my head. It's going to be partial L over partial, how do I say, A2 times partial L. Nope, partial A2 with respect to Z2. And we're just going to go on. Ooh, all the way. Oh, this is what I'm saying is like, this is where the motivation is going to end up coming from. Is, how do I say this? Is we should do W2 first. And that is that partial one from when we were reading of like, that's the upstream gradient that we're going to pass forward. And because we got it from W2, we're just going to send it to W1 and then it's just going to multiply nice and cleanly. I think that's where we're going. So I would be really happy if that works. So let's do W2 first, which means we also want to do B2 first. So we got to take it all. Oh my goodness. I'm that wiggly, huh? Wait, let's see. If I make it big. Oh, crap. Okay. My undo button does not handle scale. Okay. Move with me. Thank you. And then, bear with me now, guys. Holy cow. These things matter. They're very critical to learning. Okay. Let's do let's do L. Let's do W2 first. So we're still going to have. I wonder if anybody's making fun of my deltas. How would I properly write a delta? Surely not this. No, that's like a. Yeah, imagine it like a. That's like so much work. Okay. Is the. I don't even. I'm not even sure. I don't think. Is it a delta? Let's not worry about it. Over A2 times. Oh, but we already can't do that. Is. Oh man, and I gotta go back to the notation from class. Is you do W2 and we want to do JI. Oh, today's video is longer than an hour for sure. Um, sorry if that was loud. That's a lot of notation. Gosh. Okay. It is J times partial A2 J over partial A. No. You guys can't see what I just did, but it's very bad. Oh my goodness. I hope. I feel like my writing hasn't been that out of sync. Oh my goodness. Of course it's not out of sync because I'm looking at it on the iPad. It's probably. Oh my goodness. Has this video been horrible? If I lose everything, I have to call the video here. I'd be very upset. This is what my iPad looks like. It's split half. It's just like a finger glitch, and I'm trying to save as, and if I can't, because I'm going to swipe out of the app and reopen it. If everything's gone, oh my gosh. And that's part of the game we play. That is part of the game we play. So, wow. Just wow. Um, and what's it called? I don't even know if we don't have the time to process this. Um, huge mistake, very evil. Um, consequences of vibe coded software. Um, what's it called? There's no cache, I guess. I was really hoping there was. Really banking on that, and I couldn't save it. It wasn't saved. I go back, it's gone. So everything I just did is gone. Um, we're going to have to move this to tomorrow. Um, we were moving in a good step though. Like this is still momentum. Um, I think we were gonna get it. It would have clicked, which is a shame. A shame that we didn't get that. Um, so yeah, I think I'm gonna call my girlfriend and I think I'll make the fixes. There's like a few small things. I'll fix those, and then I'm gonna head back. So hate to do it, but it has to be tomorrow. I do think we'll get the, how do I say? We would have gotten it, and we should jump straight to it. I think. I've done it. I've done the normal linear regression to multi-headed linear regression. Now we can do multi logistic regression to neural network tomorrow, and hopefully it's just smooth flow, and then hopefully LLM. LLM is really scary because you could write it. You could write it single variable wise. And given that an LLM is like the big dog, I guess that's nice that even that part is within scope if you're willing to put in the work. Um hmm. I think it's possible. I think it's possible. I think the hard part, is that deep intuition that earlier I said I was avoiding. I think I should build it. Um like, what is an outer product, when to use it, those like new tools outside of the context of building which is bad because we're going even lower level, um, away from code. So that might have to be something that I do in parallel. Um, but practicing those, that like intuition is like, oh, so you should do this operation. Um, I think I need to build that muscle for like the just like the linear algebra. Um, where are we going to go in terms of code? Let's do that in this video. I want to look at, please don't fall. I want to look at the code for, um, let's look at the code for Nano GPT. I don't think it can be that bad. What's the speedrunning competition? Is it Nano GPT? Where's the leaderboard? It's not this one. Nano Chat. No, it's not. Nano Chat is like it's Nano Chat. Oh, it's two things at once. It's also the fact that you could buy it for $100. I see. Okay. So I just want to read the model.py. Let's see. So, ooh, wait, he built this with Claude? Interesting. Python test tasks, delete dataset, dependency by. Clean up fragile code. Okay, actual nano chat. And then common core eval. Ooh, big. Breaking chain to a large upside. Swap previous 410. Interesting. I want to look at that. Ooh, and I want to look at that. What's engine? Oh, they added flashes. Flash attention. That's whatever. Full precision. GPT. GPT is model.py. And what's engine? And what's in execution? Tokenizer, I don't care. Optima, loss eval. Yeah, those are whatever. Okay, hopefully these are all files. You guys hear that? Let's see. Document batches. I'm also sort of just trying to see like how big they are and like how complicated I think the code is. Like, could I write this? Tokenizing distributed data loader. Okay. Oh, this is if this is the data loader, I think that's good news. Data loader, not I'm not intimidated by it yet. Dataset. Dataset upgrade required. You must have a data folder that has your actual text. I find that strange. Wait, what's in scripts? What am I in right now? I'm in NanoChat. These are the scripts for you to play with the hosted thingy. See dataset. Okay, GPT. I hope this is the one that like this is the model. Yeah. And no positional embeddings. Rotary non-positional embeddings. Wow, why are we rotating for fun? QK norm, ReLU squared, no learnable parameters. Oh, y'all put learnable parameters in your normalizer. Oh, is that smart? GPT config, sequence length. Ah, see, that's bad for me. Because why sequence length like predetermined? Vocab, apply rotary embeddings. This is literally, yeah, you're rotating, but where's the other stuff? Causal self, attention, batch size, sequence length. Batch size, sequence length. D model. Oh, so you're saying C is H times D, I guess? Head times D model. So yeah, that's actually like the big one. Interesting choice. KV cache, MLP, whatever. Yeah. This is your transformer block. Attention, MLP, forward. Cool, cool. GPT. You're just gonna do a bunch of them. Parameter. Torch no grad. Whoa, that's not a small file. Okay. Engine. And you mean to tell me this isn't just like a helper? Use calculator. KV cache. Oh boy, there's so much going on. Execution. Dude. Oof. Oof. Yeah, that's no joke. um, yeah, I gotta get to that as soon as possible. Um, I'm a big fan of having my like low level intuitions. Um, but gotta start coding it up. Let's see. But let me just double down one more time of like, okay, I'm in the future. Okay. How do I want to balance what I write versus what an agent writes? This is coming to me. I'm seeing I should totally, what's it called? I should vibe code my first attempt because I should be asking for particular things to be built. You know what I mean? I should architect everything on like paper, vibe code what I think is correct, and then get brutally, just experience all the brutal lessons like firsthand and eventually converge towards nano GPT or something like that. And when I'm doing that, whatever agent I'm going to have scold me for like my architecting decisions, I want it to tell me it's going to use nano GPT or something of my choice. I might choose something like something GPT-2 focused, so that like the code being compared, that should be anchored to like the actual coconut paper. You know what I mean? It should be anchored into like what is actually being run. Did we use Torch Titan? I'm not sure for the coconut paper. If we did, coconut is meta. Must have used Torch Titan. I hope. Um, but yes, those things is like, do I even? There's so many. There's levels of understanding. Do I even understand? Remember the parts? That should be trivial to someone that like actually knows what's going on. Like, do I even understand those parts? Um, so yeah, yeah, and but that can be vibe coded. And if anything, I'm almost curious. Is like, do I ever even hand type that? You know, like hand typing causal attention. That should be like a leak code problem. You know what I mean? That's an interview question. Like I should read it. I should read it, and like because of this bottom up, I like understand it. But like, yeah, I should be vibe coding functions. Vibe code on a function level, not on a script level. And I think that is very critical. Vibe coding functions. Vibe coding functions. I think that still forces me to be in control and have like deeper understanding of like what like inputs and outputs. And like a function is going to be an isolated thing where like I say I sit down for an hour. I don't know. Hopefully not an hour. Like 30 minutes is like I really want to understand like just this function. You know what I mean? So the agent wrote it like differently here. Like why, why couldn't I do this? And then like, then that I could like retype, for the sake of the game. You know? Um but that acceleration is far better than like, I don't know, I open a blank IDE, I open Volchat, and I go, you know what I mean? Um so I'm like I'm glad that just now I'm clarifying. I do want to when I start coding soon, I'm vibe coding functions still. So yeah, like vibe code BPE. Ooh, and finally it's time to go back to the homework from my LLM class. Finally, finally, I'm just gonna go back to the actual homeworks because he gave us good homeworks, and I'm sure that will actually help me out. And I have my professor's code. That is so clutch. He said he built it with Claude, but like he built it with Claude. So see you tomorrow. It was a good one. Um, what's the thumbnail for today? This. Toodles.